As always, our recordings of our virtual meetups will be available on YouTube about a week after the meetup, and we'll post a message on Meetup when the recording's ready. I am very pleased to introduce our speaker today. Dr. Jags is an applied mathematician and data scientist with more than 10 years of experience in building software and systems. In his current role at Wi-Tronix LLC, Jags develops deep learning computer vision systems and algorithms for railroad safety and operations. He also works with researchers at IIT Chicago in developing open source quasi Monte Carlo software. Um, Today, feel free to ask questions throughout the talk. You can unmute yourselves or use the raise hand feature on Zoom, or you can put your question in chat and I will interrupt Jags as they come up. Pass it over to you.
Well, thank you, Rebecca. Thanks for the introduction. And also thank you for the opportunity to talk about it. And also before starting, I would like to thank my employer to authorize me to share some of the content that I'm going to talk about today. Okay, with that, let me start. I'm going to share just the PowerPoint. Okay, can you see my screen?
Yep, we can see it.
Okay, is that Rebecca? Is it good now? The PowerPoint.
Yeah, we can see
Okay.
it.
Okay.
It's not in presenter mode, but that's fine.
Okay. Okay. So, okay, I think it should be good now.
Yep, now it is.
Okay.
Yep.
Okay, thank you. So today I'm going to talk about the project that we are working at Wi-Tronix for this railroad crossing inspection. This is one of the very good example of deep learning and computer vision techniques. Before I talk about how we are doing it, I'm going to introduce the kind of problem, basically what we are dealing with, provide some introduction, and then try to establish some prerequisites for like deep neural networks and basically convolutional networks, and try to provide some of the examples typically used for these kind of problems. And then I will try to talk about like maybe simpler solutions and more complex solutions. And then probably then I will try to show some of the examples from my from our work actually. So with that said, yeah, as Rebecca mentioned, please feel free to stop me. Consider this is a more like a high level introductory kind of thing, more like a survey and with in the context of the problem that we are working on. Okay, so here if you see, okay, here if you see the uh, in United States, like there are like more than 128,000 railroad crossings, and about that, like 1/3 of them have gates, and with the flashing lights. There are many crossings still doesn't have a gate. Even with the, especially with the gates, there are a lot of accidents happen, and basically there are a lot of fatalities happen. So these crossings are pretty much automatically activated based on how the train is approaching and how fast. So there are some circuitry that identifies the moment the train comes closer to the crossing. So there is an inductive circuit that is built. For example, this is a crossing. Sorry, here is the crossing I'm showing. So there is a circuitry here, and that it extends all the way towards back in the track, and that identifies the incoming train, and this gets activated, right? So these are all some of the crossings that you might have seen. Yeah, and I'm going to explain about the different kind of crossing, different parts of the crossing that makes all those things make it work, right? So right? So basically, there are some. Also mentioned there are some crossings, especially in the urban areas. Like if you are going to the Chicago, especially the closer to the suburban areas, those traffic lights also linked with the traffic lights. So they work with based on the basically the train is coming. Especially you might have seen in the metro train, the train is coming. The traffic lights also gets activated, and that will basically create the red light to stop the traffic. That's what it is. So here is right. So the crossings in a typical crossings, right? You have a mast lights, and this is called the cantilever lights. Basically, the lights that is extended over the road, and this is called a mast light, right? And there are there are different kinds of cross gates. It's called two quad stands for two quadrant or four quadrant, depending on the size of the road and how basically high traffic areas either they use like two gates or four gates. I think I will have some examples to show about that, right? The requirement is, I think the gates here says before 15-20 seconds before the train reaches the crossing, the gates must be fully down, right? And also, if you already went through different crossings, you would have seen the basically the lights blinking. So uh, this is called wikivac, and I think the modern ones have these kind of pairs. They go on and off alternatively to simulate this kind of effect. Where this in the olden days they used to swing, so to create that effect, right? So basically, there are many requirements. I think that was all governed by this called Federal Railroad Administration, and they have mentioned how the traffic, what are the requirements for this traffic, basically how far the gates should extend, and what are the requirements for the gates, and what is the frequency these lights should flash. There are many requirements, right? So the thing is that the problem that we are trying to solve, right? So I talked about the crossings. What we are trying to solve is, especially my employer is trying to solve, is how to automate using this artificial intelligence, how to automate this crossing inspection to work with a human. So to help basically augment, in the sense that probably that's the right word to say, to augment, to make this inspection basically they can reduce the interval or maybe help in the inspection, and maybe more documentation kind of systems, right? So basically to help and enable so that the people can work more effectively, right? That's the kind of our goal, right? So the thing is, I mentioned like two quad, four quads. Maybe I'll show some examples, right? So these gates make sure less traffic areas, and the four gates they also block the exit side, so that you might have seen some people passing through the crossings. Those kind of things to be avoided. So another thing, the important part about this crossing is, you can see this is the sign. If there is a problem, right, the people has to call this number, right? And here it has given, for example, this MPTA. This is the railroad name, and this is the basically the crossing ID. This is the number you call, right? So basically, most of the time, right now, today, if something is fails, people call it actually, right? So we are trying to see, okay, how we can, uh, if possible, report before somebody informs it. And a lot of times, I don't know, in busy life, I don't know how many people take time to really go and inform people, right? In those kind of cases, how we can automate. Okay, so that is a kind of problem that we are trying to solve. Right here, I'm showing the what I talked about, the two quad and four quad gates, right? If you've seen, so this is the four quadrant gate. If you see, like there are gates that are blocking both in entry and exit gates, right, like that. So especially in the busy areas, right? And also there are some residential areas where they don't want to have so basically the residents, they don't want this the locomotives to blowing hard. So that kind of quiet areas, they put it this kind of crossings. And some cases, right, they will have to avoid people running through it, they will have a median, right? So to block that one. So that's the kind of setup they will have, depending on the traffic, depending on the basically uh, see, almost every crossing is pretty much unique, right? Based on how the road crosses the tracks and how many tracks are there. Like there are many things changes from one crossing to other crossing. That's the idea of the two quadrant to four quadrant, right? And having said that, let me go to the yeah. So I talked about the inspection, right? So as part of this inspection, this is a big manual. The railroad companies, they have to send personnel to inspect these crossings, like a monthly, quarterly, and annually. And basically, the quarterly inspections are a little bit lighter, and the monthly inspections are a little bit lighter, and the quarterly, annual inspections are much more rigorous to make sure everything works fine. As you can see, these crossings have to work in all weather conditions throughout the year. They cannot, basically the failure has to be so low. So this is, and also this, any of these crossing failures and that leads to any of these accidents, this is a big legal and PR issue. So the railroads take a lot of time and effort to make sure these crossings functions very well, right? So some of the requirements, for example, and again, as I mentioned, I am part of this team, and at my work, my team and the product managers, they did extensive research on how to, what are the things we can do, right? What are the things possible within the kind of setup system we have? These are all the kind of the classes from that inspection manual we figured out, right? For example, to check for like flashing lights, the voltage based on that. So using AI, how much we can do about these things, and then how the gate arm and the gate mechanism. So the gate mechanism is the one that is where the gate is attached to. There is electric motor that is operating this and this warning system. These are like high level thing, and then individual in particular, like when we are inspecting how the individual gate arms are working, and the mask light, whether it's flashing at the right frequency intervals, right? They typically flash from like 30 to 60 um, 60 per minute, right? So that's the kind of requirement they want to make sure that it's running that, and then basically whether the light pairs are working fine, and then the warning time I mentioned. So there is certain time, right? So before the locomotive starts, you might have seen the lights start blinking, and then the bell sound starts coming, right? So that starts, and then when the warning started, then the gates start coming down. There is like a choreographed kind of activity that happens. So all those things there are some huge requirements. So they have to check it. So what they do now is these people go, and there is a circuitry on the side of the thing. Maybe I will show some of the images, and they go and activate those things manually, and then check whether all those things are working. It's pretty manual. As I mentioned, in the island where the road and the track meets, there is a circuitry that extends all the way to back, depending on the speed of the locomotive. For example, right, like up to 2,000 feet, not up to 2,000. Typically, like if it is a 70 miles per hour locomotive running, then basically like up to 2,000 feet, they have to, before that the circuit should be installed. And then based on how fast train is coming, that inductance of the circuit changes. That helps them to identify what speed the locomotive is coming, right? If the locomotive is running slow, then the lights also, based on the speed, they will start activating that 15-20 seconds interval, right? So if it is running really slow, you don't want to activate much ahead of time, like people get impatient with the class, all those things. So the people have to manually check all those things. Okay, so basically the thing is, as I mentioned, so this is very important, but thing is, this is really a costly work, and it is a highly labor intensive, right? So because of that, they have to employ a lot of people to go and inspect, and also, as you know, so because it's a manual inspection, there are something could possibly be missed, right? So that's where we are trying to see how much we can help in augmenting it. Okay, so having said that, I thought I will show one crossing to understand a little bit better, right? So here I have opened one crossing here. Hopefully you can see my screen. So this crossing nearby where I live, this is called the Deal Road in Naperville. Like you can see this crossing. Yeah, before I jump into that, I don't know if anybody has any questions. I'm just going to show a real crossing here. So if you see this crossing, right? So this is like a one-track crossing here. Like I mentioned, this is a median, and we have a cantilever lights, and you can see there are one pair here, one pair here, right? And there is the huge gate arm, like to block these two lanes, right? And there is the mask lights here. right? And then I mentioned, so there is a motor mechanism here, and there's a counterbalance, right? We have that kind of setup, and then you can go here a little bit, and then you can see those warning signs. Okay. So you can see the one that I talked about, the kind of warning signs, and all those things are there. This is like the typical crossing. So, yep. So to control all those things, you can see there is the circuitry. This is what they go and activate and do all those manual inspections, right? So yeah, this is how the typical crossing looks. Let me go back to the presentation. Yeah. So basically this is the example of a two gates and a two cantilever lights kind of setup. Let's see, right? I think the kind of view, right? So yeah, my company, like Wi-Tronix, they provide the remote monitoring solutions to these railroad companies. So these cameras are installed in the like the outward facing, and they can see this kind of view, right? So this is kind of thing. So there are some videos, I think, I don't know, maybe I'll give the links later, people want to watch this kind of outward view, right? So all those crossings, right?
Yes.
Again,
Anna Marisa is asking if you collect the data from sensors in real time.
yep, yep, real time. So so the solution, the way it works is these boxes are installed on the locomotives. They can collect pretty much all the signals there. So the biggest innovation the Wi-Tronix brought into this business is, previously they used to have a recorder that records all the data. If something accident happens, like the black box kind of thing in the aeroplanes, then only they go and look at this recording. So Wi-Tronix, what they did innovation is, they pretty much in real time upload to the cloud, and the customers can watch pretty much what is happening in the locomotives, and then they can track. So right now you can do all sorts of remote, basically all sorts of remote monitoring stuff you can do. Right now we are trying to provide this pretty much real-time video. They can watch how the crews are operating and how the outward view is looking like what I showed here. So you could see this view pretty much in real time. Yeah, hopefully I answer your question. Yeah, pretty much everything is real time. So yeah, here is another thing I showed you, right? So basically this is the engineer called locomotive engineer. So here is the camera that is looking outward. I took it from YouTube. There are plenty of examples in YouTube. So this is the way you see it, and then you can see this is the road number. So the locomotive, they call the asset and ID for the railroad companies to track it. And then this is the way the engineer side. I think this is where the camera is installed. Okay, so now let's go to it. Yeah. So what we are trying to do is, using those outward camera, how much we can automate and monitor it, right? Here is something I want to show why this problem is really challenging. First of all, this has to work 24/7. It has to work all time, all weather conditions. So it has to work all the time. One good thing about this, because this is a locomotive, like a headlight in our car, there is a light facing outward. They can right nighttime, it illuminates the gates. So that's the reason we could still work on even night times, but with the visibility changes. I will have some examples to talk about. Another big challenge is, let's say this is a track, and not depending on the road how they cross it, there's a crossing angle, right? Sometimes if you think of, this is the way the gate is from here. If your locomotive is here, the gate is pretty much, basically the gate, actual gate will be hiding behind that motor mechanism that I showed. So sometimes, so basically when we have outward facing camera, when you're coming from here, you may not be able to see the gate all the time. So the reason I'm saying is, some people think, okay, why can't you just take one image and just do all those verifications, right? So it is not that a simple problem, because this has to work all kind of variations, different kind of crossing. That's the problem, right? And also, as I mentioned, we also need to check whether the lights are flashing, for which we definitely need a video. right? That's the kind of thing. So another advantage of, because we have a video, we could basically uh, accumulate output from different frames. Then you can do ensemble to get improve your overall accuracy. That's another reason why we are doing much more sophisticated solution than simple taking one image, right? So now let's go to, yeah, okay. I hope I introduced enough, talked about enough about the classic. Looks like we spent already close to 30 minutes now. So now let's get into the actual how we are going to solve this problem, right? So what we are trying to do is the deep learning, right? We are just using the outward camera, and let's see how much we can do out of that. Traditionally, I think people, if you are already working in this computer vision, you may have heard this kind of hog kind of term. This is how people used to do the computer vision, object detection, and verification kind of stuff previously. But after this, deep learning become really popular, right? So the deep learning meaning, like, we use a deep neural networks to solve this problem, right? So you give an input, you do extraction, and then it learns and gives you output. So the biggest challenge is getting the data and choosing the right architecture. Pretty much, it just simplifies the problem. Traditionally, we used to get features and then train a network. So with the latest innovations and the developments and basically availability of the more and more powerful GPUs, this is possible now. Previously, this was not possible because we did not have enough computing power. I think people who are working in this domain are already pretty much familiar with that. Okay, so I took some of these examples. I took a lot of stuff liberally from this CS231 course from Stanford course, right? So they have given a lot of nice introductions about the classification, segmentation, object detection, in such segmentation. I think if anybody wants, I will go in details, but hopefully, I think most of the people who are familiar in this field, I hope they know, understand the difference between segmentation, classification. So why we are talking about is, in our problem, we are trying to locate these gates and then verify its status. That's why we are trying to do that, right? In the object detection, right? And again, in the last 6-7 years, there are a lot of developments happened. So in a high level, right, they have like a two-stage object detection or one-stage object detection. That's the kind of solutions available. And then the faster RCN, and that's kind of revolutionized this object detection. There are so many variations, right? There are so many things available. And then the one-stage detection called the YOLO and then SSD. This is kind of the popularly available, well-researched and well-documented object detection solutions are available, right? So as I mentioned, like the single stage one, all that it does is it just takes the input and tries to give you just simply output. What is the location? Like, basically, where this object is there, you are trying to detect, okay, here is a dog, and what is the coordinates? That's what we are trying to detect as a one stage. And yeah, so this one stage detectors depends on the anchor boxes. Basically, you try to overlay different shapes and aspects of these boxes and try to detect it, right? uh, yeah, I think yeah, that's a kind of thing. Mainly the anchor boxes and those kind of things are biggest challenges for one stage. So the two stage, what it does is it has a the object detections works with the feature, right? The feature extraction, right? And then the one stage detectors typically just classify it. The two stage detectors, they get a feature extraction and then do a second level of classification. So they kind of split. The one bigger advantage is these kind of architectures are used to be typically much more accurate than the one stage. But I think with the recent more and more developments, I think the one stage also trying to beat the two stage, right? With that said, so I'm going to little bit dive into more about this one state, especially called the YOLO. Excuse me. Rebecca, can I continue?
Yeah.
Okay.
Yeah.
So sorry about that. So so I'm going to talk about a little bit about the YOLO. So this one, especially, I think this kind of architecture were popular recently because they are giving much better accuracy, and also this YOLO comes with the different levels of computational complexity, like starting with nano, small, medium, large. So you could have one architecture and you could deploy it either on a big GPU or all the way to the lightweight mobile devices, right? So that's one of the advantages, and there are a lot of community support. So that's why the YOLO is really popular nowadays. So kind of going to talk about in this context how this could be useful for our kind of right? So the YOLO architecture, right? It has a, like mentioned, there's a backbone to extract the features, and there is something called the NEG, right? That's basically the path aggregation network. And then so basically these kind of architectures are used. So previously they had like a one feature extraction and try to classify it. The problem with was depending on how the anchors was chosen, they used to work with only typical sizes of objects. So this kind of basically this upsampling and these things, right? It helps to work with the different sizes of objects, right? That's the kind of architecture we have. Okay, now let's go. This is a little bit more sophisticated view of that architecture previously we saw here. All right, here it gives you more realistic, basically using these different parts of this network, right? So these networks, right? Once you have this architecture, this is kind of loss. You are trying to this is kind of loss function. We are trying to optimize using this the optimization to get to train our model. So I'm just giving you a quick glance of basically the overall losses depends on how the objects are classified and what's the confidence, and then this is the complete IOU to get that one, right? These are all the kind of loss functions. So yeah, here a little bit more. I think if we have time, we'll come back. But basically, pretty much these networks are like have a one config file. You could configure different kinds of like as I mentioned, small, medium, large kind of network, right? So they have the bottleneck like cross stage partial networks. So you can stack depending on how sophisticated, basically how much capacity you want in your network. You could configure all those, right? So yeah, some of the hyper parameters, right? I mean, if you're in this domain, not only you have the right architecture, and also you may have to optimize depending on your data set, right? So these are all the kind of hyperparameters available in this particular family of object detection models, right? These are different kinds of augmentation features, right? Like the focal loss and the HSV hue augmentation, for example. And when you are these models gain pretty much high accuracy depending on how they augment the data, right? So the whole data. So all those things are depending on what kind of parameters you use. So basically, what I'm trying to say is, depending on the kind of data set you have, like in our application, maybe these parameters come differently, but depending on the application, these parameters will completely vary. Okay, so what we are trying to do is, like as I mentioned, so for this problem, we are going to detect the object and then look at it as a video view, right? We are trying to verify it from multiple frames. So yeah, maybe before I go into the tracking, I don't know if anybody has any questions. If there is any question, maybe I'm going to show one example how this object detection and tracking kind of could work in our application. Let's see. Here is one example I have. Hopefully you can see in my screen. Right, you can see this is the kind of crossing here. It's a simple one, and also this lighting condition is pretty good here, right? You could see the gate arm is because of the angle, right? This angle is like about maybe the 30 to 50 kind of degree angle, and you could see these gates, and then you can see this light, right? This is the kind of setup. So this is kind of where we detect multiple objects and then accumulate, basically consolidate from different frames, and then try to make one video level decision how they are working, right? So yeah, here is one example, right? So here, like the next topic that we are going to get into, right? Once you detected object, so we need to track them across multiple frames. Let's get into this now. Okay, so one very good solution available right now is it's called deep shot. So these networks, the way they do is they basically you detect the frame and then feed into this network and then try to kind of track from one frame. So there are two aspects it use. Basically the bounding boxes, like I mentioned here. So you take one bounding box and then go to the next frame. How much overlap this box overlaps with the previous frame? You use that as idea, right? And then there are two aspects it uses. One is how much overlap and how similar is from one frame to other frame. So that's the kind of idea for this deep shot kind of network. So they use, I think internally the Kalman filter is used so to track these objects. Basically, it uses this box center position under the aspect ratio and the height, right? And then these two are like the velocities of these 4 parameters. It tracks them and then try to identify these objects in a multiple frames, right? So let's go to the so as I mentioned, yeah, the same thing. So the moment you see one object right here, let's say you go all the way back, the object was never visible. I think in this video maybe it's all available, but yeah, here you can't see. So at some point of frame, the object enters in, and after some time the object leaves the scene. So all those things will be tracked based on the two criterion that I mentioned. So yeah, here is a little bit how they calculate the basically the losses, and then the distances, and then compute from one frame to other frame. So yeah, here is one basically algorithmic thing I picked it from the paper. So you try to basically try to add a new objects that enters the scene, and then delete the objects that once they leave the scene, right? And then you have two computed, right? The cost matrix and gas. The cost is like the IOU map, right? And then the gating is like how they are differing it. So those two parameters are used, right? So using these two things, you can build a simple solution. But if you want to, there are some problems with this one. Here, I think in our case, we've seen as we go here, we are in this case, our camera is moving, right? In this kind of computer vision problem, the object is stationary, but the camera is moving. So as we get closer, the angle that we see these gates, the angle changes, right? So that brings a different kind of problem. They may not look similar in certain frames. So this, because this is a two-stage detection, right? You detect and then you track. That they may not work in all the time. So that is where we need. Let's go to the. That is where you need a more like a video level object detection. So right now, these two things work separately. So the more modern approaches are like the machine. What I talked about so far is called the post processing methods. So the more basically the effective one is like you try to, like, for example, take a 3D convolutions, right? You take two frames, one frame to other frame. So instead of doing convolutions in a frame, you do straight over to video level, right? That's the kind of approach. Other thing is you take detection and then use recurrent neural networks to combine output from multiple frames and then make one decision. And then even more sophisticated things are optical flow methods. So they try to detect basically how much the object moved from one frame to other frame, what based on the light events, all those things. Then they try to estimate this optical flow using neural networks and then try to track the objects. So as I understand, I think these methods are a little bit more complicated, but they seem to work better. But I have not really much experimented, but I'm saying just this kind of things. Depending on the complexity of your problem, you could do that. So other thing approach is basically the 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 object tracking that I mentioned. So they work in separately, like you detect and then track. The maybe the much better approach is how to do them together, right? So here is another approach where they kind of same network, you try to do the detection and tracking. That's the other one. So there is another solution available. Probably this is where we will get into the demo. So as part of this, Google researchers, they developed this one, where basically you do detections and then use this LSTM kind of networks and then try to track from one frame to other frame, right? So using this one, so basically the main advantage is you don't in my previous approach, what I was, every time you do detect without knowing what happened in the previous frame, right? These things, they do a much better job because you have a context here, right? So yeah, the flow net is what I mentioned, like using this optical flow this kind of approaches. Yeah, okay. So I talked about what are things the thing, right? To measure these things, right? So the model detected one box, and then what is the ground truth, right? To measure those things, we use this kind of IOU metrics, right? And then how do we check those kind of basically how much the precision recall is computed using these things. So basically, to measure the performance, you need to measure how much the overlap is. There is a IOU threshold, and then the confidence, or how much the confidence of the object detection per object basis. Right. Okay. So before I get into this one, if any questions I can answer. Otherwise, I'll try to show one example here. So as I mentioned, the context RCNN, right? So here, I have this code example here. So these networks, right? Let me bring this. So this context RCNN, like if you want to experiment, this is part of this TensorFlow object detection framework. And here you can see this is the, so basically if you are, all that we need is that configure this config file, right? These are all the kind of parameters we have here, like right in this one. And then to train this network, what we need to do is like we need to give the checkpoint. Basically, the if you want to retrain, you will pick the one model that was already trained by this using some open source data, and then for your particular data set, you will use this as a seed and try to train this one, right? So that's the kind of setup we have. Here, what I've shown is like I took this as only demonstrating here the inference part. Here you can see basically I have installed the TensorFlow. I'm going to install the TensorFlow package here. So this brings all the yep. So it is installed here. So then I'm going to install the Cocoa tools. All right. So after all those setups are done, right? So this is the package that I mentioned, the Google Flow object detection, the research one. So I'm going to install this one. So what I'm trying to demo here is, so for this context RCNN, so we have a every frame we detect a feature, and then we try to give a additional the context information. In this case, the context information is what is the camera that took the video and what is the time. So based on the time information, it tries to keep this context, and then it remembers this in the memory. So here, let's see, it loads the model. Okay, sorry, maybe I missed something. Okay, so maybe there is something I'm missing here. Sorry about that. So after this is installed, okay, so maybe I can show the code, and then maybe we can talk about it later. So the model is loaded. So that I'm trying to show the context here. So for every image that we are having, when we are feeding through the video, right, we have the timestamp from one frame to other frame. So we are trying to embed this time, and then take this as an embedded feature, and then the input is the object location from the previous frame, right, and all those things are fed here, and then we are going to run the inference here. per image basis. So here, basically, in this demo, the input as shown is without the context and with context, right? If you show here, here is what it done. So this data set is called the basically to track the animals at the night time, right? So that's the kind of input here. So this is without any context. So this one is with the context, meaning like in the past frames, if you detected this object, the model remembers this one, right? So here, in this case, it was easy to detect it. Here, the simpler network failed to detect, but the context RCNN, it was able to detect again with much higher confidence because it knows the past. So here are some of the examples we have here. Yeah. So yeah, that's the kind of thing I want to show here. So I mean, again, as mentioned, unfortunately, I cannot use the data set from my work. So I'm trying to show it from this open source data set. If somebody wants to use, this is the way to go. Yeah. Right. So yeah. So here I have, as I've shown, here is one example, like with the good lighting conditions, as you can see, all the thing, everything you can see. But here is another example. You can see. Hopefully, you can see my video. Here is one the kind of challenges we have at the night. Basically, the foggy kind of setup here, right? In this kind of situations, you can see still the model is able to detect, and then as you can see, this 100 is this object ID. It's able to track and then detect. Right, so that's the kind of challenge here in this different kind of lighting conditions it has to work. And other things is basically you have, as I mentioned, so this is the kind of angle with this kind of angle, but here you can see this is like the 60-degree kind of angle. So I have this kind of nighttime setup, and here you have the 4-quarter lights with the nighttime. So there may be sometimes you have some kind of obstructions, right? So that kind of setups we have. So the reason why I'm saying why it is really such a challenging problem. So here is like basically much wider road, basically the 4 gates at the different locations. So almost every crossing is kind of looks different. Here again, another one with the nighttime. Again, there is a damaged gate here, right? So this is kind of time. This is the evening time. That kind of light, basically different kind of light. So the model is able to learn and detecting all those kind of changes. So here is another the snow kind of situation. We are expected still to work. So this is kind of a troubled condition where we are not able to detect at all. Right? This is a night time with the snow, and this is how the gate arm is stuck. Right? So basically, as part of this inspection, what we are trying to do is the gate arm is this is expected. This is a failure case. There has to be a real-time alert we have to give to the right. So this is
Jax,
yeah.
would you be able to share a link to the Google Collab you had earlier?
Yep. So I think I had another. Let me put it in. Yeah, I have another example. I don't know whether it is shared publicly. I will share it publicly if it is not. I had one more example to demo for the. So there is another computing architecture for the comparison to the YOLO that the efficient did, but I don't think we have time. I don't know whether we have time to check it. Other one. That's the other alternative you have, right? So yeah. So I was talking about the kind of lighting conditions, why this is such a challenging problem, right? So we are expected to work all the time. Okay. So another thing is, okay, so we were talking about another advantage of considering this is a video problem rather than the frame problem is, here I have listed the kind of object boxes here. So this is like the whole video, all the objects detected are plotted here. So if it missed in one frame, you could use it to interpolate and then catch that one. So that's the kind of advantage we have with the considering this is a video problem rather than frame problem, right? Yeah, I think pretty much I covered the important things that I want to talk about it. If anybody has any questions, I can go in the. Uh, so basically, in our kind of industrial setup, right? So we not only, it's not a one-time done problem, right? I think these kind of problems we continuously gather data and then keep retraining it. You have to take and then do. So that is the kind of implementation kind of challenges. So you collect the data and then label it and then feed it to that one, and then there is a user feedback. If there is a if there is a basically failure, you get some feedback from the user and then use it to retrain the model. That's kind of stuff. It's an implementation kind of thing. Yeah. So other things, right? One is this problem, right? The sometimes you may not have enough images for certain classes. So those kind of cases, we do augmentation, right? So with the augmentation is something like, here is one example that I copied from this here. So basically, you take the image, you the same image, you alter it, and then feed to the network. So here in this case, let's say we are only getting the images only in the daytime, but nighttime or the evening time, little bit light conditions, you could transform the images to accommodate with the little kind of variations in those lights. Right? That's the only thing you can do. Let me.
Jax, a couple of questions.
Okay.
The collab notebook needs access.
Yes, I will do that.
And then a question about how do you select the features?
So I think, not sure what you are asking, but in this deep neural network network, you don't really choose the features, right? You choose a backbone, right? And then the backbone, as you train the model, it learns the features, and then the second stage where you classify it and pick the objects. Not sure if that is what you are asking, but the feature selection we don't do here. The biggest challenge is you label it. For example, here, sorry, maybe let me show here. These are all the human labeled one, and then you train the model to pick those things. Did I answer your questions? I will try to share this. Anyone with okay, I'm trying to get the share link. In the meantime, if anybody has any other question. Okay, I'm trying to share this one also now. Okay, yeah, I think that's it, Rebecca. I think I have some more things to cover, but I don't know whether we have time here yet. So, yep. Any other question?
Okay, well, thank you, Jax, for a really thorough talk with lots of context and covering a whole breadth. You basically, covered all of computer vision there,
Mhm.
in an hour. So, yeah, really appreciated hearing your talk. Just a reminder to everyone that this is a monthly meetup, and that we typically meet the last Thursday of the month.
So I think somebody asked, how do
Oh,
you pick?
there's
How
comments.
do you
Yeah.
pick the? We pick the backbone. So basically, like as I mentioned, depending on the complexity of the problem, right? There may be a like. Let's start with the simplest situation, right? If you're if you don't have a lot of lighting condition variations, if you don't have a lot of changes, let's say you are trying to detect a box in a within a room, only one kind of lighting conditions, then you don't need actually really complicated models. But if you have the one that I showed, these kind of so many lighting condition variations, then basically the depth of the neural networks you can pick. Let's say we pick the YOLO, right? The YOLO has a different levels of sophistication, right? The like I mentioned, small, medium, large. So those things actually, that particular model, if you're picking the YOLO kind of thing, they use that the cross stage partial network. That's a backbone. But actually, you could pick, for example, the ResNet 50 or ResNet 100, that kind of backbone also you can pick it up. So it depends on the sophistication, the complexity of your problem. Maybe you can pick from the very lightweight to the all the way to the complex. But how do you know whether the model is sophisticated enough for you? One thing, right? I think some of the pioneers in this field, like the Andre Karpathy, one of the thing he mentions is if you should be able to overfit within your data. If you are able to overfit, then means your network can learn, right? That's how you pick the backbone. Hopefully, I answered that question. Thanks, Rebecca. I think that somebody was asking.
Yeah, great. Well, yeah, we're about on the hour. So it seems like most people here know each other, so if they have more questions, they can follow up with you.
Yep.
Thank you everyone for attending.
Thank you.